Okay, so this is the Steam Theorem. It's true. We proved it. So the question is what does it mean? Why is it interesting? So, you know, what's the interpretation of math? Why should we potentially care about this? Well, standard, perhaps, interpretation would be the following. We have a short schema in terms of defining length, low order. Its fitness is above average. UT of H is more of UT. That schema in the next generation will receive more samples. What does it mean to receive more samples? It means more individuals than other. And the rate in which it receives them is exponential, but I mean, this is the assumption is the theorem's only true for, tells you what happens in the next generation. The problem is in the next generation we don't know how that fitness mu t of h relative to the population fitness will change. If the population is unchanging and we have a fixed population, and it eventually has to decrease because eventually it will become the population. But the population is changing anyway, so it still may change in some fashion. But if you're willing to make the additional assumption that it does, that its fitness remains above the population average, then what we're describing is exponential growth for however long a period of time it is. Holland wants to say that this is a good thing. Why is this a good thing? Well, if you believe that this bandit analogy applies to search, if giving exponential more trials to something in the bandit problem is the optimally way to explore versus exploit, maybe this makes sense for optimization problems, but these are all maybes. This is the theorem. How far these other two things hold are going to be subject to properties of particular problems. Questions so far? Okay. The other part of the traditional interpretation of the schema theorem is if you look at the schema theorem, you go, well, if this is the case, you know, I could really make the GA perform better by getting rid of crossover and mutation, you know, because look, I'll get more schema and crossover and mutation only decrease things. So the schema theorem, crossover and mutation are only negative effects. But we use them. So what's the story of why we might use them? Well, the one reason which people often propose is the following, is kind of the classical reason to justify particularly crossover. So recalling from earlier, besides this idea that by sampling the different schema, we explore and exploit optimally, if you believe the analogy to the bandit problem. Crossover also may do the following. So let me read this to you. So just as a child creates magnificent fortresses through the arrangement of simple blocks of wood, so does the GA seek near optimal performance through the juxtaposition of short, low order high performance here, high performance being thickness larger than the population schema. So the idea, the picture that they want you to take away is the following: is that, for instance, furry by itself might be a good thing for a rabbit. Short legs might be a good thing for a rabbit. The way the population starts out, they're short schema, they can be reliably sampled, they should grow. Maybe it happens to be the case that there's no rabbits that are either furry or short-legged, but the hope is that crossover can combine those two schema. They're compatible to be joined over through schema, and then likewise that schema can now compete in the population. This is I don't have a mathematical theorem to say that GAs do this or don't do this. It'd be quite hard to come up with such a thing, but this is one justification given to GA. So this is, I guess, what we say on the next side, right? So this is pretty much what we've said already. So the idea is that the GA works by combining these schema, where we have these partially, but perhaps not completely independent problems. And these schema correspond to building blocks. So crossover combines the building blocks, which is good. You know, in the bandit problem, we said that it may be optimal to explore and exploit if your bandit problem meets certain assumptions. The schema theorem does give this exponential allocation. It's possible if things, we only prove things for one trial, but if somehow the population, it can maintain above average fitness for more than one trial, then we do have this exponential allocation. What's being combined are the schema, not the string. So this is the idea of what the building blocks are, these schema, and these are also what's competing in the crossover thing. So the idea is that crossover powers this recombination of schema. So it's certainly compatible with the schema theorem, but not proven. And if you did a brief search on the internet, you could quickly find well over 400 papers on whether crossover does or does not combine schema, where people will take various sides of this argument and show for certain problems that yes, we can prove that it combines schema, or no, on this problem where it clearly should combine schema, it doesn't. But mutation, we understand why we have mutation. Mutation is our local search operator. We clearly need mutation. We clearly need selection. Had no selection, we couldn't improve our solutions. It would be completely random search. Mutation, we get a chance to search locally. So this is what people are. There is experimental evidence that crossover helps, and so we would like to have some explanations of why crossover helps. It certainly doesn't help for all problems. This story is one explanation given why crossover helps. Now I want you to come up with another story, a challenging question I'm asking you, why crossover might help. What's another story we can tell about why crossover is potentially a good operator?
when the problems are like, let's say that when the whole problem can be partitioned up, then if because I'm thinking of the notes from actually the Gatsby course, where
Thinking about some sampling algorithm, perhaps.
where I have the diagram, I can't really show it, but if each section of the problem is separate, then crossover works because you can cross over, you can cross over and still the solution will be valid in that sense.
Yes. So this is a good point you raised, which I want to. So like a classic problem to try to argue that crossover works well and you can prove various things, and this problem's called, it's not a realistic problem, but called 1 max, but you can analyze it, where the idea of 1 max is you have a bit string and the fitness of your bit string is the number of ones in it, okay? And so your goal is, of course, to evolve a bit string of all ones. And it's very hard to show anything about any sort of thing. You can imagine that, yes, if you just had mutation, even with a high rate of mutation, what's your optimal rate of mutation? It might be hard to you're not going to cover the spaces quickly, whereas crossover, if you have some separate things where this has some ones over here, this has some ones over there, even though you have some zeros, some things are being destroyed, you can still grab large groups of ones faster than you can with mutation. So for instance, in the all ones problems, where the problems are completely separable, works out fine. More generally, you can imagine, suppose you had a fitness function. Our fitness function f looks like big F. It looks like the sum I equals 1 to k of fi x I1 to I x I to xi plus 1, something like that. I.e., it depends on your bit string. It's the fitness is made of sum of these two plus the sum of those two. If you had this completely additive fitness function, then it's kind of clear that crossover would work nicely because things are completely separable in this linear fashion. But what's the potentially negative of using a GA on such a fitness function if you knew that it had this property? Your fitness function is additive. You can separate it into k parts which are independent and they correspond to independent parts of the chromosome. If you didn't want to use a GA, how might you optimize this? If it's completely additive, i.e. things are separable, the value of this doesn't subtly influence the value of that, then it makes sense to actually solve each problem independently. You're not wasting any time. So this is kind of the story about GAs is you want things to be separate, but if they're completely separate, there's no point in using a GA. But you need some separation for there to be some meaning to crossover. It just can't be 100% crossover, or you're probably not choosing a good algorithm. But this is a story of how crossover is possible with this building block hypothesis, i.e. that you can combine separate sections well. What might be another reason that crossover works well? So to think this through, consider what happens with crossover as your population, maybe it's evolving and it's starting to become quite uniform, versus crossover at the beginning of the run, where you have a whole bunch of different bit strings in your population.
You're going to save a good pass.
Yeah. So expanding on what you said is that towards the end of your run, let's take the extreme case. All the individuals in the population are the same. What will crossover do? Absolutely nothing. What will mutation do? It'll do just as much as it did at the beginning of your run. So just like in simulated annealing or other things where you think, well, maybe it's good to have an algorithm where you search a lot in the beginning and search around a little bit less towards the end, crossover gives you a natural way of doing annealed mutation. At the beginning of the run, the effect of doing crossover is likely to be very strong. As your population has more and more similar strings, the effect of crossover becomes less and less and less. So another alternative explanation sometimes given about the usefulness of crossover is it's kind of a way to do mutation that's annealed, that's self-tuning. Okay. Other questions? Okay. Story of why GAs may work. As we've said, this is another result which I'm not going to present is so the idea is that with the schema, the population GA you can view as working on individual schema. Population samples a lot of schema. The idea is that somehow the GA is implicitly parallel since these traits are evolving independently. There can be many more traits in the population. There can be individuals. But of course, if your schema are large and they have high order, they're not really sampled. So rather than saying, if you have a population of size L, rather than saying something like L to the 2n or 2 to the n, things are usually sampled under some set of assumptions. It seems like roughly cubic in the population size traits are sampled. Not something I would examine you on. Okay, so Holland presented GAs along with the schema, a book that's even nice now to read it, Adaptation, Natural and Artificial Systems. Goldberg had one of the first really nice applications of GAs to oil wells. Here's just two papers, I think, taking different perspectives on crossover. Here, this is it's an influential paper. It's discussed in the Melanie Mitchell book. If you grab this fitness, where they basically show something wrong with this building block interpretation, some problems where you'd expect schema to work, but they can show and build higher order schema, but they show that it fails to work on this problem. This is a paper on the other side where so this is crossover wasn't so essential in building higher order schema, where this paper shows an example where it is. There's many such papers, but if you're interested further in this, I think these are two nice starting papers. Okay. Understanding GAs. I think it's important to know what the NFL theorem is. NFL theorem, extremely influential in evolutionary computation. Go ahead and discuss what it is. We don't actually prove it, but download the paper, you can read it. It's fairly intuitive result. They introduce a lot of notation to prove it. The NFL theorem is the following. And we'll look at it more formally in a moment. The basic idea is, given any two optimization algorithms A and B, the performance when averaged over all optimization problems is exactly the same. So basically, if A performs well on some class of problems, then there exists an opposite class of problems such that B outperforms A. Depending on, it's not so influential in machine learning, but there are plenty of NFL type results for learning results. Course compression, somehow it's not surprising that given a random text you can't compress it. Okay, so to make sense of the statement and how it's what he's saying exactly, we have to define what we mean by an optimization problem, an algorithm in this context, and performance. Okay, so we'll look and see what Woolport and McReady are arguing. And you first read it, it's quite disturbing to people. What do you mean? I take any two algorithms and they perform exactly the same on average? Why choose any algorithm at all? Let's discuss it as we go along. You say your GA should have crossover. I say my GA should have mutation. And you know what? It doesn't make a difference because of the NFL theorem. You hear these statements sometimes. Okay, so what is the NFL theorem? So let's explain the notation to make those words mean something. Optimization algorithm for us is the following. We're going to assume it's deterministic. You can change it to a randomized algorithm and have more results. You just have to be a little more careful in the notation. So imagine you have your GA, you think, oh, it's random. Well, maybe you have a pseudo-random number generator. Another thing which is a little unusual, but we kind of need it for the comparison, is it's non-revisiting. Am I missing a slide in notation system? I think I should.
Notation 1.
Thank you. So here's the theorem. Actually, that's not notation 2.
No.
So there should be a notation 1, right? Here we go. I somehow got these out of order. Notation 1. Okay. So our model is as follows. X is our search space. This is this landscape that we're always talking about. Under the assumptions X is a finite, we're going to be searching in a finite space. Y's are the values that we're trying to optimize. We assume Y is a finite set, where Y is some subset of R. It's kind of hard to change this theorem, even though I suspect there are things to infinite sets when problems come up. So the set of all optimization problems is just Y to the X, i.e. that's all possible landscapes. So imagine a very simple landscape, which is maybe where I'm standing here and here. Each of these lands, at each position you can have, say, 4 possible values. So all possible landscapes correspond to this being, for instance, 1, that being 2, and that being 4, that being 3, that being 1, this being 4. So this is just Y to the X, and so that's also corresponds to how many optimization problems there are. Okay. So a particular optimization problem, a particular landscape, is something that maps the set of the landscape's positions to values A is what we're calling an optimization algorithm. What do we mean by an optimization algorithm? Well, an optimization algorithm A, when applied to a particular problem at step L, is the following. So AFL gives us the output of the algorithm, the first L outputs of the algorithm. So for instance, the optimization algorithm, like imagine gradient descent or a GA, moves around in the landscape. So first we're in position 1, and we move to, we're in position 1 and we're at value 5. Then maybe we gradient descend a step and we don't have a gradient, but somehow we end up in position 2 and we're now at value y2. And so forth. So the first L steps, the output of the algorithm are the positions that the algorithm goes to and the output of the algorithm. Okay. So AFL is just giving us the L positions and L values of the landscape at that position. Questions on this notation? Okay. So the algorithm moves through the space X, and it's at a height L. Visualize. Further requirements we put on A is that it's deterministic, which can be relaxed, non-revisiting. What do we mean? We mean for our optimization algorithm, if I start at this position, my next output, I never return to that position. Maybe this seems unrealistic, because you imagine a lot of algorithms you might use, like a GA or some sort of random search, you go back to the same position. But we make this assumption because we can turn any revisiting algorithm into a non-revisiting algorithm, in the sense that if we ever go to a position we were at before, we just don't output it. We wait till we get to some new position to output it. Okay? So it's just a way to kind of improve the algorithm. The output at algorithm at time L plus 1 is just the previous position up to time L plus the new location that we have. The algorithm depends only on the sequence that it's seen so far. Somehow we avoid weird algorithms which somehow depend on the future. It's a function of where you've been so far. It can't depend on the future. Okay, to measure the performance of an algorithm, performance is just any sort of function from y to the L for any L into R. So for instance, you can imagine if we're doing straightforward optimization where we're trying to find the best solution, well, the performance of a given algorithm at time L is just the best solution it's found so far. But you can have other performance functions. Maybe you're investing money or something, and it's it doesn't matter necessarily that you found the very best by time L. It's just that overall you've done pretty good. So maybe you want to use the mean. This can be any. The results are going to hold for any function v of y. Questions? Okay. Maybe before we do the theorem, we should think a little bit about it in terms of a GA, since when you first look at a GA, it doesn't fit in this model. I mean, you have to make it fit in the model. How is a GA potentially an optimization algorithm under this definition? Okay, let's assume that our random number generator, so it isn't random, it comes from some fixed thing. Then when we generate our population of n individuals, that's the same as taking n search steps, because we've touched n landscape locations. Every time we get a new fitness value and location, that's a new position in, it's a new value for AFL. So every individual that we evaluate a fitness on, every x that we touch corresponds to the next point in our search space. So if we do that, we can see how a GA fits into this framework. Questions so far? Okay, so what's the theorem then? The theorem then is the following. You give me two algorithms, x and y. Sorry, maybe this wrong. Yeah, so given a fixed landscape x and with a fixed outcome value, given a space x and a space y, algorithms A and B, then if we look at the performance, or we look at what the algorithm does at time L, we have the following observation. The number of landscapes for which algorithm A's fitness value is the vector y is exactly the number of landscapes that B's vector of fitnesses or values y is the same. I.e., what are we counting over? We're counting over all possible landscapes. If we count over all possible landscapes, even though algorithm A and algorithm B will do something different on any particular landscape, when we count over all possible landscapes using the previous definition, just as many algorithms, just as many landscapes F result in a sequence of fitness values y as B does. Okay. Visualize the following. Algorithm A moves through a fitness landscape in one way. Algorithm B moves through a fitness landscape another way. In terms of a function y, those just correspond to the heights. So imagine some vector y, y1, y2, just looks like the heights of the fitnesses. So this is perhaps some travel. This is 1, this is 2, this is -1, this is 4. You give me any such fitness vector y, A will have a trail through its landscapes just as many times with y as B will. So now, recall that a performance function is a function on y, so that's, for instance, max or mean. We just now observe that if we sum over all the fitness functions, the value A of f of L and the value B of f of L have to be the same, because of this property that the number of f's for any given y is the same for both of them. So better performance by an algorithm A on a given set of problems, on a given set of landscapes, if this is doing better on some set of landscapes, say f prime, well, somehow this has to make it up if these two sums are equal. That implies that there's a set of problems such that B outperforms A. Do you believe this? Do you think it's true? What's the intuition about why it's true? Yes?
Because nearly all algorithms we see.
Can you speak a little bit louder? I'm so sorry.
Because nearly all algorithms we see, if you look at, are very good at mainly what they do. We're effectively told about them in a certain context, as it were, in a certain scenario. And so they are usually good for that and that surrounding set of problems. However, you also find that there's an awful lot more out there, and that they are usually, or they're not always taken across and used for those as well. So it's, to me, it seems just sort of almost commonsensical in a way, that you're going to have, it's all going to even out in some way, but it's certain things are either made or are better for one thing, but not as good for another. I'm explaining this very badly, but
I think you have to have the right intuition. Can anybody elaborate on that intuition a little bit? Yes.
You might say you had an algorithm that optimized the traveling salesman problem. You
Yes.
mean by a different set of problems, you mean by maybe one algorithm might be better for less than 10 cities or something, and then one might be better for between 10 and 20. Is that what you mean?
What I'm meaning is, and what the theorem's proof for is exactly when our algorithms are when our set of problems is defined as this set y to the x. Where, x is some finite set. So for instance, it has x1, x2, dot, 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 xn, let's say. And y is some set of finite values, let's say y1, dot, 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 yk. A given problem is simply, looks like a given x with any given y, a given x with any given y, a given x with any given y. How many such problems are there? Well, there's y to the x such problems. So well, in terms of seeing the way the theorem works, you can see it in the following sense that for those of you who maybe think about Bayesian probability, one way to think about this is we're doing things over the space of all problems. Each of these problems, which corresponds to one possible landscape sampled from this set of y to the x, is a situation we're in for a given optimization problem. After I've seen x1, x2, x3, what can I derive about the next one's y value? Can't derive anything. It's uniformly as likely to be y1, y2 as yk. There's no, I see 4 more steps. I still can't, the Bayes optimal classifier would still predict that my next location is y1 through yk with equal probability. There's no way to gain traction. When we consider the set of all problems, there's no assumption made on this structure. So it's the space of all problems, the way we've defined it, is completely without structure. If you said suddenly the space of all traveling salesman problems, each instance X kind of has a connection to the Y. It's not arbitrary. There's some smoothness between the X's and the Y's. Here, there's no smoothness anywhere. You just have, it's like you play a guessing game. Oh, I'm flipping a coin. What's the next value that the coin is going to be? And you actually know that the probability is heads or tails. There's nothing you can do. You're not, oh, I've had 1,000 heads in a row. I better guess ahead. But it really is 50-50. It's the same scenario here. Each landscape is uniformly likely. No matter how much information you have, there's nothing you can do on the next step. So you can do whatever you want. That's kind of the intuition. Had a large impact, this paper. Because there are a lot of papers about genetic algorithms saying, oh, crossover is good. Oh, you should do crossover this way. But people saw this perhaps as a criticism that how can you decide one algorithm is better than another based on a small experimental comparison. I think, unfortunately, that sometimes the algorithm, this result is interpreted to mean that, well, all algorithms are the same and there's no meaningful way to compare them. As you pointed out, and you pointed out, is for a class of optimization problems, if you say all TSP problems, somehow all TSP problems doesn't correspond to this model. There's still some sort of smoothness between the X's and the Y's. Saying something's a TSP problem makes an assumption on it. You can imagine that if you do have TSP problems, and you have your TSP problems are drawn from each value on the edge is from some finite set. It does define something in this model, but then you have other problems which look like anti-TSP sorry, that's completely unclear. But basically, once you assume a class of problems and there's some structure on the X's and Y's, the result doesn't hold. Okay. Questions? Okay. Let's see how we're doing. Okay. Let's take a final quicker break, and then we'll start on applications that have been quite influential in genetic algorithms. Take maybe a 7-minute break.